Hi. So, welcome to the second class in the series on group theory. So, what we are going to start off with is basically definitions of groups and understanding what groups are, the properties of groups. And this is going to be the video in a sequence of videos which will cover all the aspects of group theory for master's maths programs and basically as a preparation for IIT JAM 2024. So hopefully this will be useful to all of you, and please like and subscribe to the channel, like the video, subscribe to the channel. That will help me continue this series. And yeah, so let's get started. Uh, we are going to talk about what groups are. So we'll start off with the definition of a group. So this is the definition. A group is a set G with a binary operation. With a binary operation. What is a binary operation? A binary operation is an operation that acts on two variables. So when you do an operation, you operate on two variables. This operation is a binary operation. So a group is a set G with a binary operation. Let's call it a dot such that the following properties are satisfied. So x dot y belongs to the set G if x belongs to G and y belongs to G. So this says that as long as both x and y are elements of the set, if you operate x dot y, or if you use the binary operation on those two elements from the set G, the output, which is x dot y, also belongs to the set G. So you cannot end up going outside the set G if you take elements from the set G and use the binary operation. So we call this property and we say that the operation, the set G is closed under that operation. Set G is closed under the dot operation. So you cannot end up with an answer which goes outside the set G if you start off with two elements from set G and use that operator on them. So that is the first property. Then the second property is the associative property x dot y dot z should be equal to x dot y dot z for all x, y, z belongs to G. So this is associativity. So this is standard in many uh, other sets. So for example, integers and all, you can integers, at least the multiplication is associative. So this property tells us that the choice of the place where you put the parenthesis doesn't matter, right? The third property that is characteristic of groups is that there exists an element E belonging to G such that for all x belongs to G, for all x belongs to G, E dot x is equal to x dot E is equal to E is equal to x. So this is existence of identity element. Existence of identity element. So basically E is the identity element of the group where whenever you apply a property on the identity element or you do the operation using a particular element of the set and the identity element, when you operate on them, then you end up getting that same element back. You don't get a different answer. So E dot x and x dot E gives x, right? So this element E is called an identity element, and this is true for all elements for all x in G. So no matter which element of the set you take, whenever you do E dot X, it should give the answer X. So that identity must exist. And lastly, the fourth and final property is for each X belongs to G, there exists X inverse belonging to G such that X inverse dot X is equal to X dot X inverse is equal to E. So this is the inverse, and the inverse also exists. So for every element X of the group, you should have another element in the group which is X, which is called X inverse, which is such that the product of X and X inverse is always going to give you the identity element. So basically, a group is a set G with a binary operation such that all these four properties are true. The first property was the set was closed under the binary operation. Basically, if you operate on two elements from the set, you cannot end up with an element which is not part of the set. The second property was associative property, where we apply the operation on three elements, then the choice of the order in which you apply the operation doesn't matter. X dot y dot z is the same as x dot y dot z. The third property was that there has to be an identity element in the group. What is an identity element? An identity element is a number like 1. So if you think of the set of integers, and if you take 1 as the identity element for the set of integers under multiplication, it makes sense because anytime you multiply 2 into 1, you end up getting 2. 3 into 1, it's 3. So for all elements in the set of integers, if the operation is multiplication, then 1 is the identity element because you can multiply anything with 1 and it will give you the same answer, right? The last and important property that has to exist in the set is that for every element there has to be an inverse. An inverse, what is an inverse? Inverse is something where if you multiply an element with its inverse, you should get the identity element. If you use the operation dot operation on two elements, one of them is X and the other is its inverse, you end up getting the identity element. So this is the basic definition. We'll see examples and try to understand groups in more detail. But for now, just make sure that you understand all the four important properties of groups. Moving on, what we will see now are some more properties. The first one is the identity element. The identity element of a group. And the group will be denoted like this: G dot is unique. So there cannot be two different identity elements in the same group. If there is, you can prove that if there are two different identity elements, you can prove that E will be equal to E dash. So I'll leave that exercise to you. We will spend some time doing problems, but today's class will be more about theory. The next class will be about discussion of problems, and we'll discuss some proofs in group theory, and that will help us get acclimatized to how to solve problems in this subject. But for now, we'll just focus on the theory. So the second property is given a group G dot and an element X belonging to G, there is only one inverse. There is only one element Y such that Y belongs to G basically, and Y dot X is equal to X dot Y is equal to E. So this is the definition of the inverse of X. What this property is saying that the inverse is also unique. Inverse of an element is also unique. You cannot have two inverses for a same element. Again, this is something that you should be able to prove yourself. And if you're struggling with it, like please mention it in the comments. We will discuss the proofs in a later class. Third thing that we want to talk about is a basic definition. A group is said to be abelian. A group G dot is called an abelian group if it satisfies the commutative property. So x dot y is equal to y dot x for all xy belonging to G. So if the operation of the group is commutative in nature, commutative means the order of the operation doesn't matter, x dot y is always equal to y dot x, then the group is said to be an abelian group. So this is just a definition. And some notational issues that we will talk about right now is some notational conventions. So we have been using groups like this, where the operation is this dot operation, where we write x dot y when we say we are operating on two elements x and y. But it is annoying to keep writing it like this. So many times people drop this dot. So instead of x dot y, people will write xy. And the group operation is written like a multiplication basically. So this is multiplicative way in which you are writing the group operation. However, you could also have convention where group operations can be written in an additive way. So what is an additive way? So you will write instead of x dot y, you will write x plus y. This is an additive group. So the plus operation is taking the place of the dot operation. So this is additive style of writing the groups, right? So we can reframe all the group laws in additive notation. So for example, if we have a group G plus, right? This is my group. Then what are the four properties that groups must satisfy? First of all, x plus y should belong to G for all xy belonging to G. Notice here we are operating the plus on the two elements x and y, and we are saying that x plus y should also lie in the group. So this is saying that the operation, the group is closed under the plus operation. This is the first property. The second property was the associative property, but now we'll use the additive notation. So we'll say x plus y plus z should be equal to x plus y plus z for all x, y, z belonging to G, right? So earlier we were writing this like this. The meaning is the same, we are just using additive notation now. We were writing this earlier like this, right? The third property is there exists an element 0, an element 0 belonging to G such that for all x belonging to G, 0 plus x is equal to x plus 0 is equal to x. So here 0 becomes the identity element. Earlier we were using E for the identity element when we were writing it in multiplicative notation, right? Now we are using additive notation, but the idea is the same. Again, finally, there is an element for all x belongs to G, there exists an element minus x belongs to G such that x plus minus x is equal to minus x plus x is equal to the identity element which is 0. So here minus x is the inverse. Earlier we were writing x power minus 1 as the inverse when we were using multiplicative notation. But in terms of additive notation, these are the four properties of groups. I hope you are getting the sense in which we are writing these group properties and the notation that we are using. If you have any doubts and all, please ask in the questions in the comment section, and I will try and respond to that in the next few videos. The next thing we are looking at is a couple of examples of groups. So for example, non-zero rational numbers, non-zero rational numbers, Q star basically, under the multiplication operation. Under the multiplication operation is a group, right? Why is it a group? You can think about it. Try and think of all the properties. So if you think of the first property, is the set closed under the multiplication operation? Yes, because you can take any two non-zero rational numbers p by q and another r by s, and the product pr by qs is also a non-zero rational number, right? So there is no issue here because by definition q and s are non-zero because it's a rational number, and the overall p and r are also non-zero because the set has only non-zero rational numbers. So the product of those two is also an element of the set. So operation is definitely closed under multiplication. The second property is the associative property. Again, we can say P1 by Q1 dot P2 by Q2 dot P3 by Q3 will be the same as P1 by Q1 dot P2 by Q2 and dot P3 by Q3. That is obvious. So the second property is also true. The third property is there is an identity element of the set. 1 is the identity element because anytime you multiply p by q with 1, you will end up getting p by q itself. So 1 is the identity element of this multiplicative group. Usually when there are multiplicative groups, 1 is the identity element in such groups. And finally, the fourth property, you can say that p by q belongs to G, then there is q by p belonging to G also, such that p by q multiplied by q by p is equal to the identity element 1. So q by p is the inverse of any rational number which is non-zero. Since it is non-zero rational number, you can actually invert it without worrying about p becoming 0 in the denominator. Otherwise, if it was including 0, this would not have been a group. If it was the set of rational numbers not non-zero, right, which includes 0, then you would not have an inverse because for the rational number 0, there is no inverse then, right? So as long as you have non-zero rational numbers, there is an inverse, and therefore the whole set forms a group under multiplication. I hope this is clear to everyone. Another example, similar example that you can think of is non-zero real numbers, also non-zero complex numbers under the multiplication operation are also groups. So this is the set of non-zero reals, and this is non-zero complex numbers. These also form your groups. Okay, we'll go ahead now and we'll discuss some more properties here. But we'll start off with a definition. The number of elements of a finite group is called the order of the group. Is called the order of the group. What do we mean by finite group? Which finite group means the set is finite. its cardinality is a finite number, right? If the group has an infinite number of elements, has an infinite number of elements, it is said to have infinite order, said to have infinite order. Okay, so this definition just talks about order of a group, and that is pretty straightforward. The number of elements in the set G is the order of the group G. So you can have finite groups with finite order and infinite groups with infinite order. Let's look at some more properties now. Let G be a group. Then the following are true. Then the following are true. For A and B belonging to G, if AB, product of AB is E, then we can say that A is equal to B inverse and B is equal to A inverse. So as soon as you have A times B becoming E, or basically becoming the identity element, then each of those elements are inverses of each other. The second property is AB's inverse is B inverse A inverse for all AB belonging to G. This can be proved pretty easily. You just multiply AB inverse with AB and see whether it is becoming E or not. It will become E only if you write it as B inverse A inverse. So you need to know about this reversal of order. So AB's inverse was, you write it as B inverse A inverse, not A inverse B inverse. The third property is inverse of A inverse is simply A for all A belonging to G. And the fourth property here is for A, X and Y belonging to G, if AX is equal to AY, it implies X is equal to Y, and if XA is equal to YA, it implies X is equal to Y. So these are what are called our left and right cancellation laws. So just like in basic algebra, we can cancel some terms here. As long as all three elements are members of the group, we can say that if AX and AY are matching, then you can cancel off the A from the left and X will be equal to Y. And similarly, if XA and YA are identical, then we can cancel off the A from the right and X will be equal to Y. So these are my left and right cancellation laws. The second set of properties that we want to look at are about powers of an element. So powers of an element. So when I say x power s, what I mean is I am doing the operation x dot x dot x s times, right? So from this it follows that x power s, x power t will be equal to x power s plus t, because you're just doing the operation many times, s times here and t times here. So the total number of times is s plus t. Also, you can prove that x power s power t is equal to x power st, and x power minus s is equal to x power s power minus 1 and also equal to x inverse power s. So these are similar to the laws of identity that we have, laws of indices that we have in lower algebra. Also, x power 0 will give you the identity element E for the group, right? Now, we look at something where we figure out the order of a particular element of a group. So we say let X be an element of a finite group G then the powers of X cannot all be different. Cannot all be different. Why can't they all be different? Because if powers of X are all different from each other, then the number of elements will become infinite, right? If X is an element of a finite group G, then the number of elements of that group is finite. So if the powers of X are all different, we know from the first property that X dot X should belong to G if X belongs to G, because the group is closed under the multiplication symbol, right? So X square should belong to G, and similarly X square dot X will belong to G if X and X square belong to G. So X cube should belong to G, and so on. What we are seeing is that there are so many different powers of X, and all the powers of X should be part of the G set, right? Then what will happen if the group is finite? The number of powers of X should be infinite, right? You can go on and on. X power n should belong to G and so on. These elements are infinite, so they can't all be different because the group is supposed to have only finite number of elements, right? So I hope that part is clear, that the powers of X cannot all be different, right? And there is a smallest positive integer k such that x power k is equal to e, right? Now this is basically happening by the well ordering principle. Since the powers are not all different, then there will be some power which will become same as the identity element. X power k will be e, and after that the powers of the elements will keep repeating, right? So if suppose x power 4 was equal to e, right? After that x power 5 will be equal to x power 4 into x, which will be x, and x power 6 will be x power 4 into x square, which will be x square. So if x power 4 was equal to e, then after that all the powers start repeating again, x, x square, x cube, and again e. So there must be a smallest positive integer k such that x power k is equal to e by well ordering principle, right? Now what we can say is, now we can define the order of an element x. Once we have understood this concept, we can now define order of an element x. So I'll write the definition in the next page. So order of an element. Notice that this is different from order of the group. Order of the group was pretty simple. It was the number of elements in the set G. And groups could have finite or infinite order, right? Order of an element, however, is not the same as order of the group. So what we will say, an element X of a group G is said to have finite order, if x power n is equal to e for some n greater than 0. The least such n the least such n is called the order of x, right? So basically, some power of x has to become e, and the least power where x power n is equal to e, the least n where this happens, is called the order of the element x, right? If no such n exists, if no such n exists, we say that x has infinite order. It might be the case that there is no such element where x power n is equal to e. And in that case, what we mean is that x will have infinite order because there is no way the powers are repeating in that case, and the group also has infinite order then. Because if you don't have x power n is equal to e, the number of powers and all will never repeat after that. It will keep increasing powers and you will never come back to the e and then start off again in a cycle. So such groups have infinite order and the element x also has infinite order here, right? Let's look at some more properties to try and understand this a little better. So let G be a group let x be an element of G with infinite order, that means there is no n which is finite such that x power n is equal to e. So let x be an element of G with infinite order, let n be an integer, then x power n is equal to e if and only if n is 0. The only way x power n will be equal to e is if n is 0, because x is an element with infinite order. So technically you cannot have a x power k equal to e ever happen where k is non-zero. Right? The only way it will happen is if capital N is 0 in that case, because it has infinite order. The second related property here is if x belongs to G with finite order n, then x power n can be equal to e, x power capital N can be equal to e if and only if small n divides capital N. Small n divides capital N. So if x cube was equal to e and basically order of x was 3 small n, then obviously x power 6 will be equal to e also, because x power 6 is x cube into x cube and that is e into e, right? But x power 7 will not be equal to e, right? Because 3 does not divide 7. X power 7 would have been what? X power 7 would have been x power 6 into x. So it will be e square into x, which will be x. But that is not same as e, because 3 does not divide 7. So I hope that is clear to everyone, that if the group element has finite order, then it can be raised to a power capital N and it will be equal to e only if small n, the order of the element x, divides capital N, right? You should take some examples and then it will be clear to you. Then another set of properties here is let G be a group if an element x has infinite order, then all the powers of x are distinct. Because it is never going to become e ever, so it cannot repeat. X are distinct. This we have already discussed, so I'll not spend too much time on that. Then we have if an element X has finite order n, finite order n, then x power r is equal to x power s if and only if r is congruent to s mod n. So as long as both of r and s have the same remainder when divided by n, then they are similar types of numbers. They are in the same residue class. So then the x power r and x power s will also be the same. So you can say, so powers of x repeat in cycles of n, cycles of length n. So if any two numbers are in the same residue class, you will have the same power resulting. Then we can write, if x belongs to G and has order n, if m and n are relatively prime, then x power m has order n. So x, the element x has order n, and you take any other integer m that is relatively prime to n, then x power m will also have order n, right? This is like saying if order of x was 3, so x cube was e, and you say x square, what is the order of x square, right? So you have to do x square power k should become e. So that means x square into x square, or you can say directly x power 2k should become e, but that will only happen if 3 divides 2k. 3 divides 2k and 3 cannot divide 2, so therefore 3 divides k, right? So the smallest k that can come is 3. The smallest k will be 3, and therefore x power m also has order 3. Here 2 and 3 were relatively prime, so therefore that is happening. If you don't understand this right now, please let me know in the comments. We'll discuss problems like these in the future and it will be much clearer, right? Again, another property that is similar, if x has an order n and x belongs to G basically, if n is equal to st, then x power s has order t. Again, it is a similar property based on number theory. We'll look at problems which exploit these properties in future sessions. Another property is, let G be an abelian group. G be an abelian group, and let AB, let B be elements of G, be elements of G, having orders m and n respectively. And if m and n are relatively prime, then AB has order mn, and if L is equal to LCM of m and n, then there exists an element of G with order L. Again, the proofs of these properties, I want you to look at the proofs yourself and see if you can do them. If not, please let me know in the comments and we'll discuss the proofs in detail. That concludes the class for today, the theory session for today. What we'll do in the next class is we'll practice some problems and try and reinforce these concepts in greater detail. So the next class will be a problem solving session based on the properties that we discussed today. And hopefully you'll be there for the next class. Also, please like the video, subscribe to the channel if you like the content, and I will provide a lot of uh, free content over the next few months. It will cover all aspects of your bachelor's and master's programs in maths. So we are going to do group theory right now, and then we'll move on to real analysis, linear algebra, differential equations, and so on. So a lot of great content coming your way. Please like the video and subscribe to the channel. That's all for now. I'll see you in the next class.